Hello students, welcome back. We went through compound interest model. Now let's go to logistic growth model. Logistic growth model is used for population growth and stabilization in a closed environment. For example, if you have a deer population in a certain island or something, and if you grow some bacteria in your lab, those kind of things follow this model very, very well. Now, if you have open border, things are a little bit different. And please make this observation here. When t goes to negative infinity, and let me expand the font. When t goes to negative infinity, so we go way past, then we have negative, another negative, so we have positive infinity there. And e to the positive infinity is infinity, humongous. So denominator gets humongous. So the entire fraction goes down to 0. Now what if t goes to positive infinity? There's already negative there. So we have e to the negative infinity, and that's 0. So this part is 0. So this part just drops out, and we have e. And that is the equilibrium. We can visualize like this. Actually, this is an example that we already went through in lesson 13. So to the left, we have horizontal asymptote y equals to 0. To the right, we have horizontal asymptote of y equals to 500, the numerator. That's the equilibrium. So stabilizing population. And then initially it may grow really slowly, but suddenly it takes off, and then later on it slows down and stabilizes. And t equals to 0 is not the initial stage, but the initial stage of the observation. So whatever happened in past is negative t. So things will go back to negative infinity, at least theoretically speaking. This kind of thing applies to not just population model, but a lot of other things as well. Spread of infectious disease in epidemiology, and spread of rumors in social network in sociology, including fake news, disinformation, things like those. Speaking of those disinformation and epidemiology, I cannot but make some connection with COVID. And as a matter of fact, being a mathematician, I was impressed. German Prime Minister Angela Merkel actually brought this formula and explained that to the people and educating those people. And it was an impressive show as a leader, and I really appreciate it as a mathematician. And at the same time, our president, then President Trump, simply saying, oh, it'll go away. I was really disheartened being a mathematician. Anyway, logistic growth model is extremely important in terms of application, so it is worth studying. Here are a couple of examples. A herd of deer is introduced onto an island. The initial population is 500 individuals, and it is estimated in the long run, sustainable population is 2,000 individuals. The size of population is given by the logistic growth function given as follows. I got this problem from a certain textbook, but I thought initial population for 500 was kind of ridiculous. If you're going to introduce some different species or reintroduce extinct species into a certain environment, you're beginning with something like 10, 20, 50, not 500. That's too expensive. Anyway, I got it from the textbook, so I offer no apology here. And let's find out, or let's estimate the population after 1 year, 20 years, 50 years. All you have to do is calculate this thing with different t values here. T equals to 1, plug it in, calculate. T equals to 20, plug it in, calculate. T equals to 50, plug it in, calculate. Just calculate your work. I'll leave those details to students. do it on your own. So we get 515,149, so about 515 individuals, and then about 552 individuals, and then 1,422 individuals, approximately speaking. You don't really have to be really accurate. This thing is just estimation. Now, backward problem, a little bit more important. How many years later does the population reach 1,500 individuals? This type of problems are important. Let's go back to the previous section here. We had just straight ahead calculation, and then we had how many years later problem. You see, the second type of problem was more important. We have to solve an equation. The same goes here. Just straight ahead calculation, no big deal. How many years later? That's an equation. How do you do that? That's basically this problem. That is 1,500. It's this type of problem. Let me expand the font a little bit. And of course, nothing is going to be accurate, so let's rewrite like this. So what do we have? We have an exponential equation to solve. How do you solve this? Good question. How do you solve it? Solve for exponential, and then take the logarithm. But first, looks like we can do some simplification. Remove these two zeros. So what do we have? Okay, all right, divided by 100, we got that. Looks like we can simplify even further. Both of them are divisible by 5. So 4 and then 3. Okay, all right. And then let's solve this equation. So 3 times 1 plus 3 exponential of negative 0.04t is equal to 4. And then break up the parentheses. And then solve for exponential. All right. I squeezed in a bit too much in a single line. I shouldn't have done that. Stop at here, and then the rest, I'll do those in separate line. Okay, we are up here. Now, we solved with respect to exponential. What's next? We have to remove the exponential. We do it by taking the log. Here in lesson 14, just consider natural log. Wait a minute, in this case, it is going to be natural log, of course, because we have natural exponential here. So no problem there. E to the negative 0.04t is equal to log of 1/9. And the log and exponential cancel each other out. So this is whole thing is going to be, oh, never mind. Let me write one more time. I lost all my font. Let's rewrite it. Okay, this is what we had previously. By taking the natural logarithm, you can remove exponential and then divide by negative 0.04. T is equal to log of 1/9, which was there before, and then divided by negative 0.04. And of course, you can calculate it with your calculator. If you do that, what do you get? Log of 1/9 over negative 0.04. Punch in the calculator. What do you get? Are you also getting 54.9? About 55 years? So it'll take about 55 years until the population reaches 1,500 individuals. Okay. Does this look, it doesn't look realistic actually to me. I mean, population growth is really slow here for deer. Anyway, and I got it from a certain textbook, and that textbook probably didn't really consider all those realistic numbers either anyway. Numbers may not be really realistic, but model itself is highly realistic. Here's another problem. Again, this is written in terms of population model, but it can be used for spread of disease or spread of rumors and things like those as well. The population in a lake, oh, excuse me, what population? A fish population of a certain species, I think. I didn't write everything down, apparently, and I made a mistake copying from a certain textbook here. Anyway, a certain fish population, all right, and then we have this model, and then we have to answer these questions. The initial population, plug in t equals to 0. Population after 10 years, plug in t equals to 10, and that long-term limiting value, t is going to infinity. That's interesting. That's going to infinity. T is going to infinity, so e to the negative infinity, because negative is already there. Excuse me, a little bit bigger font. You see, negative is already there, so this whole thing is e to the negative infinity. So this thing goes to 0. So this entire thing goes to 0. So you're going to get 8,000 over 2. So you're going to have 4,000. Previously we had 1, but here we have 2, so things are a little bit different. Let's see. Do we have all those here? Yes, we have this computation stabilizing around 4,000, the equilibrium. Okay, those were easy. And then how about the other direction? How many years later will the population reach 2,500? Excuse me, 2,500 individuals, 2,500 fish. Sorry about that. A lot of typos, sorry. How many years later will the population reach 2,500? Okay, basically we are doing this equation. This is equal to 2,500, and then we are looking for t value. Set up the equation, okay, here, and then go ahead and solve it. Remember the three-step process, denominator first, and then parentheses, and then like terms. And then in the end, you'll have to take logarithm to remove the exponential. Good luck. Did everybody try and complete? Stop the playback and do it if you didn't do it yet. If you did, well, okay, here we go. Set up, simplify, and then remove the denominator, break up the parentheses, solve for exponential, and then take the log of both sides. Log of 0.4 is just a number, so don't panic. Just divide away and then run your calculator. I'm getting 24.76, 24 and a quarter, maybe just 25, depending upon your point of view. Yeah, I'll say 25 years. Okay, so much for section 2.